we ready?
Yes. All right, I forgot I was supposed to be here. Well, welcome back, everyone. So James is giving the second talk today in the series. So, welcome.
Okay, thank you. Okay, so now today we get to the good stuff. Yesterday was mostly just setup. Okay, so let me remind you what we're doing. We define the family of functions, which are the quadratic multilinear functions that are non-negative on the discrete cube. This, and then we require them to be degree at most 2. Okay, and then from this we define the matrix. Let me write the matrix in the notation of a function. It's a non-negative matrix, which is just it takes a function from this class and an input and divides it. So this is the matrix we talked about last time. You don't have to remember actually the motivation for this matrix, but it doesn't come into play anymore. But the point is, it's a slack matrix for the correlation polytope. And so if we can prove a lower bound on the positive semi-definite rank of this matrix, then we prove that by the semi-definite generalization of Yannakakis' theorem, we prove that there is no small PSD lift of the correlation polytope. Cannot be characterized by the feasible region of a small semi-definite program. And so that's our goal. Prove that the PSD rank of that matrix M is, okay, for now let's write large, in a second we'll write down a theorem. Good, and let me remind you what it means. So that if rank. So if the PSD rank is M, it means that we can write the matrix as trace AF trace times BX, where A is mapping into, so here we'll remember also the notation, A is mapping into R by R symmetric positive semi-definite matrices, and B is mapping also into the same mapping inputs to R by R matrices. Okay? And so our goal to show this is large is just that to show that any factorization of this form, it must be that R is quite big. Okay? And the ultimate goal, which is actually still open, would be to show that in fact R is at least C to the n for some constant C bigger than 1. What we'll be able to show is that it's at least 2 to the n to some power. Not the power of not. Okay, so this is the setup. So what you can do is you can say, all right, we need to think about now what are the hard quadratic functions going to look like. And if you remember, I told you that Fiorini et al. Proved that a lower bound of the non-negative rank of this matrix. So they proved that rank plus of M is at least C to the n. Or some C bigger than 1. So the first thing you might do if you were trying to prove a lower, I'm dropping money all the time. You would think it's a sign that I would have a lot of money, but actually this is the only money I have. I keep dropping it. I'm going to start with that. So thank you whoever found my money outside. Okay, yeah, so what you might do is you say, okay, well, it's more difficult to prove a lower bound on PSD rank. Let's look at the quadratic functions they use to prove this non-negative rank lower bound. Well, essentially what they did is they showed that you can find inside this M a copy of the unique disjointness matrix, and then using the techniques of Razborov, you get a lower bound fairly quickly. But the underlying quadratic function that they use is this one. Or this one and some things related to it. And already we see that there's no way we're going to be able to, so let's review it, but there's no way we're going to be able to prove a PSD rank lower bound using squares of linear functions. if you remember last time, this lower bound is equivalent to proving that that these things cannot be generated in the sum of squares cone of a small dimensional subspace. But of course, the squares of linear functions are exactly the sum of squares cone of the subspace generated by the degree 1, the degree at most 1 monomials, well, x1 up to xn and 1. And therefore, you're not going to be able to get anywhere using this f. So just to be clear, so just so you can understand what's going on here, let's just check that you cannot get anywhere. So what should you do? When I say this f, I mean any square of a linear function is not going to work. Okay, so let's define b of x to be this matrix. So, okay, so this is an n plus 1 dimensional vector. Okay, so it's the entries are the ij entry of this matrix is xi xj, and then we also have the constant term. So there's the I n plus 1 entry of this matrix is xi. And now the point is that if we take any, let's use trace for the PSD in our problem. Okay, so first of all, this is a rank 1 positive semi-definite matrix, has one eigenvalue and it's positive. It's a norm squared vector. Okay, if we take any other vector v and we consider this trace, then this is so what is this? This is trace of v transpose x1 transpose, which is just the standard Euclidean inner product between v and this vector squared. And what is that? That's sum I equals 1 to n vi xi plus vn plus 1 quantity squared. So you see that by plugging in various rank 1 matrices here, you get the square of any linear function. Okay. And the rank we used here was just this thing is sitting in n plus 1 dimensions. So if you only consider the submatrix here, which is given by squares of linear functions, then you're out of luck because that submatrix has PSD rank n plus 1. You can generate every square just by, you tell me the function, I'll choose my A to be this rank 1 matrix that gives me the function. You tell me the function you want to be squared, I choose the A, so the linear function, I choose the A so that we get this. Okay, so we're not going to get started like this, and of course you can also see that in a similar way, if we wanted to generate the squares of degree at most d functions, then we can do it using about n to the d dimensions. Because instead of just putting the degree at most 1 monomials, we would just have a longer vector consisting of the degree at most d monomials, and then we would be able to generate squares of degree d functions. So the upshot of this is that before we can talk about the lower bound on PSD rank, we need to prove a lower bound on a simpler notion, which is just, we need to show that you can't write everything here as the square of a low degree polynomial. If you could write all of these functions as the square of a low degree polynomial, then you would get a low rank factorization. So degree d corresponds essentially to rank n to the d, because that's the number of monomials. Does that make sense? So the claim is now that before we study PSD rank, we should at least understand the following concept, which is the sum of squares of degree. So the sum of squares of degree of f is the minimum d, so that f can be written as a sum of squares of degree at most d polynomials. And what we showed here for sum of squares of degree 1, but holds more generally, is that if this thing was if everything here had sum of squares of degree at most, say 10, then the PSD rank of this matrix would be n to the order of 10, so n to some constant. Okay? And we're trying to prove some much stronger lower bound. We want to prove that it's not a polynomial. So the first thing we need to understand is this quantity. Unfortunately, well, we've already seen in some previous talks how to deal with it. The polynomial we're going to consider is this knapsack polynomial. is g of x, the sum of x1 to xn minus n over 2 squared minus 1/4 for n odd. And the point is here that when n is odd, this sum is an integer, so it cannot be exactly n over 2. You have to miss by half. So this will be half squared minus a fourth, which is always at least 0. Okay, so the point is, certainly on Rn, this thing takes negative values. Just choose every xi equal to a half. This thing will take value minus 1/4. But on the discrete cube, it can only take positive values because you have to miss n over 2 by at least a half. Good. And in fact, you can see from this argument, well, okay, at least for symmetric functions, we would need to take something which is non-zero somewhere on our end in order to get a decent lower boundary. So it's good that we're taking something a little trickier. Fortunately, as was proved 2 days ago, we know the sum of squares degree of this thing, or at least a very strong lower boundary. Right? So Grigoriev proved that the sum of squares degree of this g is at least the ceiling of n over 2. Okay, so this is a very strong lower bound. Because I mean, if you trace through this argument, you're going to need like if you really wanted to have B here be able to contain all of the n over 2 degree squares, then you're going to need 2 to the n over n dimensions. So it's not going to be a very good factorization. Okay, so so and now as I was saying sort of yesterday, we just want to do the same thing that we saw Laura do, which is kind of amplify this sum of squares degree lower bound to a PSD rank lower bound, and in fact using the same method, which I guess we call relativization. So now, so now let me tell you the goal. So now I'm going to use this G, or in fact any G, to identify sort of a submatrix here and we're going to prove it has a large PSD rank. Okay, so here's this G, but now let's consider any G from 0, 1 to the n, okay, which is just non-negative, and some n, which is at least m. And then we'll define this matrix M, N, G. Okay, so it's going to be indexed by subsets of n coordinates, and also by elements of 0, 1 to n. And it's given by, so at a subset S and an input X, you just, right, so G is a function on m bits. So you just take G and evaluate it at the coordinates of X, but restricted to be in the set S. Right, so G is a function on m bits, m is smaller than n. X here is on n bits, so you just evaluate G on the restriction of X to S. So this is a same kind of thing we saw before. These were called selectors there. But that's the definition of that. The idea is, I mean, we have n things here, right? And so now, for every subset S of size m, we plant a copy of G there. So we just sort of plant G all over the space. And what you should think is, what we're trying to do here, we're trying to enforce is, notice, as we said last time, sorry, we'll try to fix this. Okay, I think it's going to be better. As we said last time, this family is symmetric under the action of the symmetric group. I mean, symmetric, so it's invariant. So if you act on the coordinates by permutations, the family doesn't change. And if you could say that the factorization respected that invariance, okay, in the sense that basically when you acted on, well, in this setup, it's not so easy what it means to respect that invariance. So just take that as an intuitive thing. If the factorization respected that invariance, respected the action, then it would be easy to prove a lower bound. So, so what we're trying to do is sort of, by hiding G everywhere, we're basically trying to force the factorization to at least be kind of symmetric. Sort of to kind of respect the symmetries. You know, like it can't concentrate on any piece of the space because we've hidden the hard instance everywhere. If that didn't make sense, it's okay. I don't know if it makes so much sense to me. Okay, so now here's the main theorem that we want to prove. And again, this is joint work with Gavendra and David Storr. Basically, whenever G has a large sum of squares degree, this matrix has a large PSD rank. So let's. So you have the setup here. So I don't want to rewrite the setup, but I'll be careful about the quantifiers. So there exists a constant C depending on G. So we're given this G such that for all n, which is say at least 2m, the PSD rank of this matrix of restrictions of G is at least, okay, so this C, remember, it depends on G, n over log n to the, let's say, 1/4, more clearly, 1/4 the sum of squared degree. Okay, so for any G, there exists a constant depending on G, so that if we let n become larger and larger, the rank of this matrix grows like n to the sum of squared degree, okay, divided by 4. And by the way, just a simple observation, actually we already said it, is that, maybe, yeah, maybe up to a +1 or something in the exponent. This lower bound follows easily from what we already said. If the sum of squared degree of G was small, then we could just have B contain all of the degree D monomials, and we would have an upper bound of the rank. Okay, so this is also kind of tight, but the interesting direction is this side. So in particular, it says that if G is quadratic, then this M sub ng is a submatrix of M, because it's just a evaluation of quadratic functions at the inputs, and therefore now you just think in the following way. This shows that this thing has to grow faster than any polynomial. That's all it shows. It doesn't show any super polynomial growth, or it shows super polynomial growth, but not something explicitly faster. Just because what you do is, for every degree, if you want to prove it grows faster than n to the 100, well, take G with some m large enough that m over 2 is bigger than 400 or something, and plug it in here, and then as n goes to infinity, this is growing at least like n to the 100. Okay. I just wanted to say that, and the reason you can't get from this exponential lower bounds is because of this dependence on G. So the point is, since this depends on G, this constant C also implicitly depends on n. So if you try to take n and m going into infinity together, then this doesn't say anything. And so to prove stronger lower bounds, you need to pay attention to what's going on with this dependence. We'll talk about that later. But for now, this is the goal.
I missed how this matrix is related to that one.
Okay, good. Thanks for asking. So the point is, if G is quadratic, then this matrix is just we could instead of thinking about it this way, we could just define GS at x to be just define this function. So if G is quadratic, then this thing is quadratic. So this matrix is just every S gives you a function. So this matrix is just the evaluation of quadratic polynomials at inputs. So it's this matrix contains all of the quadratic polynomials. So this is a submatrix. So we prove a lower bound in this submatrix, we get a lower bound here.
Thanks.
James, I'm so confused about this.
Okay, good. No, no. Please.
So G has n variables, right?
M.
M
So it's M. So sort of this time is important on this section of the board. So here we were with n, but then in order to say the theorem, so the point is this is some G. If you want, you can give it a specific name, the knapsack G. And then below this line, now we say consider any G. But now this G is on n bits.
But you're evaluating it on n bits.
No, we're evaluating it. So here we have x has n bits, but we only evaluate G on a subset of bits that are in the set S. So sort of the input has n bits, but then for every subset S of size m, here's a subset S, we just evaluate G. We evaluate G on only those n coordinates. So it's like, so it's sort of like this picture. On every subset of size m, we sort of plant a little copy of G there. You can do this. So this one, the point is that this GS here that I defined is on n bits. So what you can do is just define G sub S on n bits as G applied to the restriction, and then you're just evaluating these things. But yeah, the point is to sort of put G everywhere in this space. And of course, I mean, this is something we need to do. If I just have a single polynomial, I cannot sort of, then of course it's like trivially, the matrix corresponding to a single polynomial would have a rank 1 factorization just using that polynomial itself. So we need to have a large family of polynomials. And, okay, this is the family. And the claim is that if G has large sum of squares degree, then you get this amplification. Now, okay, so in other words, if G cannot be certified by squares of low degree polynomials, then there is no small family, there's no small subspace of functions that can certify all the restrictions of G. Yeah.
So red part of the theorem is trivial, or?
Yes. Yes. I mean.
And what does this smaller tilde mean?
This is just the dimension of the degree at most d polynomials.
And so this sign, I mean, with greater. Or
yeah, it means that you have to. What you really need to do is sum the binomial coefficients. You just sum and choose k from k equals 0 to d. So this one is just saying, listen, if you don't, that's okay. So we don't need to write it, or we can just write it formally. That this is.
Okay. Okay.
And okay, maybe from this form it's also more clear why it's true. If G has only degree, okay, we didn't say what is degree D here, where D is the sum of squares degree of G. So if G involves only degree D things, then this matrix M only involves squares of degree D polynomials. And so just using this construction, but now putting all of the degree D monomials there, right? This is just the moment matrix that you talked about yesterday. You would upper bound the rank by this. Okay, so this is now the goal. Okay, so we have so good. So Grigoriev has already supplied us with this hard function G. So now how are we going to use it? I want to use it like how I mean, sort of. We want to basically we're going to try to argue in the following way. We can prove that G has a large sum of squares degree. Well, because by assumption it has a large sum of squares degree. But, I mean, of course, there's no assumption here, but intuitively, the way you get a lower bound is you assume G has a large sum of squares degree. So we have some bound in the sum of squares degree of G. So we have a way of lower bounding the sum of squares degree of G. We now want to lift this lower bounding method to lower bound the positive semidefinite rank. So for G, things are pretty simple because so let's define D to be. There's like so many D's. This one is this D is just an aside, like it's not supposed to be. It should have vanished once we talk about it. Let's define this to be the degree minus 1. Okay. So now if we consider the cone of degree D sums of squares. Well, by definition, G is not in this cone. Sum of squares degree is D plus 1. Okay. So now we can separate G from this cone, and I just want to state what the separator should look like. So it's there's a hyperplane separating G from this cone. What does it correspond to? So it means that there exists a function on 0, 1 to the n, such that I want to have three properties from it. So the first one is just a normalization property and also a chance to define the inner product. So here, this is but this inner product is the inner product of functions on 0, 1 to the n according to the uniform metric, right? So f and g, the expectation over uniform x, f x, g of x. That's the inner product I'm referring to here. Just the inner product on functions. And this is the constant one function. So this is just a normalization. That's good. And then I want this thing to be negative at g. Okay. So the thing is going to be non-negative on the sum of squares cone. It's going to be negative at g. So in particular, it will be a linear functional that separates g from this cone. But by standard sort of conic duality, every linear functional that separates g from the cone, sort of can be looks like this. And this is let me say it anyway. This is the only way. The existence of such a phi is the only way that g can be separated from this cone. And okay, so the third property is that on the cone we should be non-negative. And of course we know what the extreme rays of the cone are. So we'll say that if we take a degree at most d polynomial and square it, then we should be non-negative. So this is a separating functional to separate g from this cone. Like without loss, these are the only proofs that separate g from the cone. Number one, you get to ignore it's a normalization, but the inner product with g is negative, and the inner product with every low degree square is non-negative. Okay, that was easy. Now I'm going to use this. Okay, there's one thing where you should be confused, and I would agree with you that this should not be n. It should be m. G is living on functions on 0, 1 to n, not 0, 1 to n. But yeah, right now we just have g. It looks like this. We assume that the sum of squares degree is d plus 1. That means there exists a separator. Okay, so now let's try to use this separator to prove that the non-negative or the PSD rank of this matrix is large. So let's write down a factorization. Okay, this should be. So let's just assume we have a factorization that looks like this, where A is mapping subsets of size m to R by R PSD matrices, and B is mapping elements of 0, 1 to the n. So we assume this, we try to prove that R is large. And in fact, I want to try to prove it in a similar way. That would be great. By, at heart, I'm sort of an analyst. And this is a sort of algebraic condition, right? I mean, the fact that the rank here is small. What I would really love to do is be able to just do the same as the proof we did for G. So, what does it mean? It means that somehow we would have a cone here. We would say, here are the PSD rank R matrices, and then I just want to show that this thing is not. I would say here's this cone, and now maybe I take this phi and I lift it somehow to get a separator here. Does anybody see sort of a problem with this strategy? I mean, there's a fundamental reason why this strategy cannot work.
Your steering R does not form a cone?
Yeah. If you average two PSD rank R matrices, you will not get another PSD rank R matrix. The PSD rank might become 2R. So, I mean, this is bound to fail. A different way of saying this is that I mean, every non-negative matrix is in the cone of rank 1 TSP matrices. You just write it as the sum of over every entry of the matrix. It has only that entry there and zeros everywhere else. Those are rank 1 TSP matrices. Okay, so the point is, here we're not going to be able to get off the ground like this, but let's do it anyway. Okay, so I want to do one thing. I want to show, we've already seen it, but it's going to be helpful. I want to show that if this B, and I'll give the definition in a second, if this B is the square, if this is a matrix, but if this matrix is the square of a low degree matrix, I'll define the degree for a matrix in a second, I want to say that then this factorization cannot exist. And we've already seen that because it's going to be because G does not have small sum of squares degree. So let's prove that this cannot be the case if B is the square of a low degree matrix. And I'll define what that means in a second. And then we'll see how, what we need to do to prove it in a general case. And of course, we'll have to address this issue that the proof we're about to use is going to be separating the two sides by a linear functional. And in general, that will not be able to work as you find. Okay, so let's define, we have a function from 0, 1, and n to just symmetric matrices. So remember, this is just a set of symmetric matrices. This is it's not a definition, that's just sort of. So given f, let's define the degree of f. And I'll write f of x just so it's clear that sort of this is meant to be thought of as a polynomial, as just the maximum degree of any entry. This is an R by R matrix. I just defined the degree of this thing as a multilinear polynomial to be the maximum degree of its entries. And then here's the claim. Let's give this representation a name star. So if the degree of the square root of bx is at most d, then star cannot hold. Okay. So square root now refers to the positive semidefinite, the positive semidefinite square root of the matrix. So this bx is a positive semidefinite matrix. You can take its square root, in particular, just by diagonalize and you take the square roots of the eigenvalues. The positive square root. So this is a matrix valued function. We can talk about its degree, and the claim is that if the degree of the square root is small, then this cannot be. So in other words, if b is a low degree square, this factorization cannot exist. And the reason I want to do that is just to see the form of the separating functional that we're going to use in general. So let's prove the claim. Yes.
So f is a polynomial?
I mean, every function here is a polynomial of degree, of degree. So f is just a function, but its entries are just real. The entries are just real numbers. So we can. One nice thing about working over the discrete cube, or general, everything's a polynomial. So degree makes sense for any function. Okay, so let's define phi sub s. So again, this is a function on n bits. Remember, phi is the separating functional for g in m dimensions. The definition is just the same as we did for g. So just you restrict phi to the coordinates in s. The point is that this is if I want to argue about some specific subset of m things, then this is going to be the functional that separates on that subset. Okay, and now let's apply a linear functional to both sides of this expression. So first, let's apply it to the left-hand side. I'll explain what this notation means right now. Okay, so we apply it to the left-hand side. In general, when I write expectation over S, I mean a uniformly random subset of size M. When I write expectation over X, it's a uniformly random element of 0 1 to N. So basically, yeah, okay. So this is the function node which maps the pair Sx to phi Sx as a linear functional on this space of matrices that sort of are indexed by sets and bit strings. Okay, so now let's evaluate what this is. Okay, so this is not supposed to be particularly interesting. It just sort of gets everybody in line with the notation. So just because remember the entries of this matrix are exactly G restricted to S, and so in fact let me just also right now write the definition of this one, X restricted to S. And so you see that this is just the inner product of phi and G in m dimensions. Just because it's just the average of the inner product over and over again with different names, because we do it on every subset of size S. But it's just n choose m copies it's the average of n choose m of these things. Let's see this thing. Okay, so the point is this is less than 0. So I'm just saying that sort of if you think about this functional, it just does the lower bound proof for G on every subset. So it's like, I mean, it's kind of the natural thing to do. This thing proves that G cannot have low sum squares degree. So if we take this functional, then it's saying wherever for every copy of G, okay, it's proving the lower bound of every copy of G. There's a little bit of of course, it's sort of now it's not so clear things would be great because maybe some copies of G can cheat as long as they're compensated for by other copies of G where the inner product is positive. But no matter what, this expression holds. Let's apply it now to the right hand side. And the goal is that in applying to the right hand side, we should get something that's non-negative, and then we separate it into two sides under our assumption on this degree of probability. Okay, so we apply it to the right hand side. Phi as X. Trace as Bx. Okay, so we can write this in the following way: so that average first over x, then we'll average over x. We'll look at phi as x. Okay, so let's do it this way. This is, I just wanted to make sure we get the intuition here right. So let's choose y to be a random bit string on the coordinates in S. Okay. And then we're just going to choose this x in two phases. First we choose the coordinates in S, and then we choose the rest. And then we'll choose x, but here we'll condition on the fact that the restriction of x to this set is equal to y. Okay. And then in here, I guess for now we still just write the same thing. So I didn't do anything. It's the same expression as before. I just first chose the bits in S and then chose the bits outside of S. This is a restriction here. There's so many. Like this is conditioning. This is a restriction. Okay. Now the point is that this thing doesn't depend on anything outside of S. So actually we can just pull, this is just phi of y. So this is now phi of y times, and let's pull this expectation inside the trace sort of for fun. expectation over x of b of x conditioned on that inside, that we see the right thing inside y. Okay, so I did two things. First of all, I said this only depends on the bits in S, so I bring it out. And then I just brought this averaging inside the trace, which is a linear function. Okay. The main point here is that since this thing only depends on what's in S, now you can think about this as a function mapping y. It's a function on m bits. It's a function mapping y to the average of b of x, where you average over all the other things. So, necessary to do this? No, that's okay. I feel like this is it makes sense, but I feel like it's too complicated of an expression. Like maybe we don't need to do it. So sorry. Like they give me this one liberty to do something less complicated. Let's do something slightly less complicated and hope that it works. Just because this is supposed to be easy, so having all of these, averaging over all kinds of different things, it seems crazy. Let's just do this instead and see if it works. Let's write these are two positive semi-definite matrices. Let's write this inner product as the square of the Frobenius norm, where I remind you that the Frobenius norm of a matrix A is just here over the real, so it's just the sum Aij squared. Okay. So does everyone believe this formula? Inner product A and move. Okay. So the point is that all of these functions are so this is I claim okay, so the point is this is a real number now. It's the Frobenius norm squared. This is a sum of squares of degree d polynomials. Okay? And the point is that we've assumed that the degree of the square root of that was d. So what does this thing look like? Again, I'm not good at multiplying matrices, so I think it probably looks like square root a s in the ij entry, square root bx in the ij entry squared. Like this is the Frobenius norm. So it's a sum of squares of low degree polynomials. This thing. I just did matrix multiplication here, so it's like the ij entry. Is this true? Say it again. There's probably. Say it again.
You just sum over I and K.
You think I should sum over? Let's see.
Outside.
So there's so first of all, there's a bunch of indices, right? So that's good. No, not enough, right?
Yeah.
There should be more indices. You said too many. Let's say here we should have K, and then of course we'll get the expression of the same form, but this is probably more like what it should look like. And if you maybe with the indices switch, but I'm bet like the fact that matrix multiplication has this artificial asymmetry, like there's this arbitrary symmetry breaking, it's confused me forever. So like why is it like that? I'm still confused. Okay, but regardless, so this thing is if you sum over all the coordinates, what's the coordinate? It's the inner product of the ith row here and the jth column here. Which is the correct thing. So this is everything correct. If I had stayed in high school, my teacher would be proud. All right. They didn't kick me out. Okay. good. So the point is this is a low degree square. So then, but the point is that the inner product of this thing with any low degree square is non-negative. So the point is that the claim is that okay, now this thing is non-negative because this is the inner product of phi with some low degree square. Let's see if people are willing to buy this. It's true, it's just the case that there's also a lot of other averaging going on, but that doesn't affect the fact that this thing is a low degree square. Should we write we can write out the full expression, that's what I was doing before, but I just don't know if it's germane at this point to, okay, why did I erase that? That was true. Does this make sense, or you want to? We can.
No degree on x, of course, that's the only input. But then s is a thing that is average over.
Right. So the point is that whenever you fix s and you average over x, you're just taking the inner product of phi with some low degree square, and that's always non-negative. So like yeah. So just fix x, and now you see okay. There's the. It's not quite the okay. So what's really happening? Fix s. Now you average over x. Only the things in S matter. So all of the averaging outside of S is just going to come inside, and you're going to get an average of low degree squares, which is also a low degree square. Okay. But again, the point here is that this is just many inner products of phi with various low degree squares. So it's non-negative. When we actually do the real analysis soon, we're gonna. When I say real analysis, the actual analysis, soon we'll open it up. But I just want to sort of, I just want to suggest that this functional is good for separating at least this matrix from factorizations where b is the low degree square. Okay. And well, maybe we'll regret not doing it later. So if somebody wants to do it, we can write the lines up. Should we do it? People, I don't know if I don't know if it's boredom or malaise or those are the same thing or confusion. Okay, but it's definitely true. This is just a restatement of the fact that G doesn't have. I mean, the point is we just hit G all over the place. So at the end of the day, we're claiming actually that G in many spots is a low degree square, and this functional tells us that actually nowhere is G a low degree square. So okay. The main point though is that this is going to be we're going to average against this kernel. That's what we're going to try to do to separate the two sides. The problem, as we already said, is that it can't possibly work in general because since the set of low PSD rank matrices is not convex, it shouldn't be that you can separate the two sides with a linear functional. Okay, so now we can give the sort of the proof outline for the whole proof. The main point to take away there is that if b is a low degree square, this factorization doesn't work. Okay. So here's the proof outline. For the theorem which is here, this theorem. Okay. So first of all, we have to. This algebraic condition is not good because it's not closed under. I mean, PSD rank is not closed under taking convex combinations. So the first thing we want to do is instead work with some kind of analytic relaxation of PSD rank. So we'll define. It's not going to be a norm, but we'll define something such that sort of every low PSD rank matrix is very close to a matrix of low analytic PSD rank. But then the analytic PSD rank will be a convex function. So it will be then we'll be able to. And in fact, this is the place that we're going to use the fact that the rank is small. And after that, we're not going to use the fact that the rank is small anymore. Second step is that if we have a low analytic PSD rank factorization, it implies that the function, the right-hand side b is has high quantum entropy. So, we're going to define it, of course, but of course, if we normalize this thing so that eventually we'll think about this B as sort of a classical quantum state. So the point is there's n classical bits, and then we have a r-dimensional PSD subspace. So it's sort of like a state that has some classical part and some quantum part. And then if we normalize so it has trace 1, so this is a density matrix, then the claim is going to be that the quantum, the von Neumann entropy of that state is very large. That's how we're going to use the fact that that's how we're going to use the fact that we have small analytic PSD, right? Okay. The third step is just that high entropy B can be approximated by a low degree square. In fact, let me say that instead of saying low, let me say by medium degree square. Okay, so now you can see the point here, which is that we can separate low degree squares. Right? We can prove it doesn't exist for low degree squares. So now we first make the factorization a little smoother, then approximate B by a low degree square, and then run through the same argument, but hope that the errors are controlled. The problem is that here you won't get a low degree square. You won't get something less than B. It will just be a medium degree square. And then the last part is where the random restriction comes in. So in fact, the whole point of this random set S and there the idea is going to be that if B can be approximated, by a low degree square, then everywhere, then for most choices of a random subset S, when we sort of restrict our attention to S, the degree will drop drastically. And then on most S's, we will see a very low degree square. So sort of we'll get some intermediate degree, and then random restriction will lower the degree. And so then on most S's, we'll be able to carry out this argument. And of course, then there's an error coming from the S's for which it doesn't work. But that's the outline. Let's at least do part one. Did we start 5 minutes late? Sorry. Sorry, let me try that again. Sure, we started 5 minutes late. Correct. Okay, so let's and let me give you some. First, let's define a notion which will be an analytic proxy to rank, although it's not quite strong enough. But then you'll see what this kind of thing means. So I want to define. Okay, so if I have just a symmetric matrix, let's define the. Okay, so this is the operator norm, the spectral norm. So this is the largest eigenvalue in absolute value, and we'll use A star for the trace norm. So it doesn't. We're only gonna apply this to positive semi-definite things. So it's just the trace in that case. And the eigenvalues are positive. So there's the spectral norm, the operator norm, and the trace norm. So now let's define the following quantity. Gamma. So let's say where it's defined on. It's going to be defined on. PSD matrices. So gamma of A is the minimum value, let's say the minimum of, okay, I see what all right. So I got confused for a second. So this is, everything here is fine. But let's not define gamma on PSD matrices. Let's just actually define gamma for our matrix M. So that we avoid introducing extra indices. But it makes sense for any matrix. So what is gamma of n? It's the minimum of gamma such that we can factor. Let's use P of S and Q of X here. So that we can factor this thing into P's and Q's. All those are PSD matrices. But importantly, I'm not putting any bound on the dimension of those matrices. So you can have dimension be as large as you want. Okay. And then what is it? It's we want all of the So you look for a factorization of M. I'm just using the same indices as we had there. Really, you can put I and J here. Probably we should have done it. Okay, but let's not do that. So for any matrix, we look for a factorization. We don't bound the dimension of the matrices involved at all. Okay? But we require that the product of the trace norm and the operator norm is at most gamma. And now 2 points about this. First of all, gamma is convex. So the point is that if we look at n plus n prime over 2, then okay, we want to claim that this is at most the average of the gamma values at n. So if if we have n given by p and q, and say n prime given by p prime and q prime, then what we should do is we should define a factorization of, we should define this at Sx to be trace of what? So, like gamma p of S, gamma prime p prime S times 1 over gamma q of X, 1 over, this is a diagonal matrix, 1 over gamma prime q prime of S. So I just did these of course these were PSD, so I can take their diagonal matrix as PSD. And then maybe we should put half on both of those. Okay? And the point is now the factorization works because we get half PS QX and half P prime Q prime. And then just to make sure that the gamma doesn't go up, what you do is just you adjust gamma and gamma prime so that the operator norms of Q and Q prime, so that the operator norms of both of them are the same. And then what you'll see is that basically you and then you'll just get that it's so like suppose the operator norms were the same of Q and Q prime, then you would just take gamma and gamma prime to be 1. So if Q and Q prime have the same operator norm, then you take gamma and gamma prime to be 1. The operator norm of this thing remains the same, and now the trace norm of this thing is at most half the trace norm of this thing plus half the trace norm of this thing. So so sort of if you insist that say the operator norms here were each 1, so that you push the value of this thing into the trace norm, then you see that it works. And in general, you just choose these weights so that the operator norms of those two things are the same. But this is like these factorization norms have been studied for almost 100 years now, say in functional analysis, and they're very useful. And in particular, thinking of them as relaxations of rank is a useful thing. And so now the last thing I want to say is, okay, so why is it relaxation of rank? So the point is here, if by the way, you see that the whole key was that we increased the dimension. So it's sort of like if we were studying the PSD rank, this would be a Harville transformation. We just increased the rank by 2. But for this, the operator norm, the factorization norm has it's convex. It's remaining bounded. Okay, so here's sort of the idea. Now let's go back to our matrix. And just notice that in any PSD factorization, there's a degree of freedom, which is that we can replace A of S by, let's say, J transpose, and replace Q of X by J, the inverse transpose. A and Q is such a weird, sorry, better cut through the speed. By J inverse transpose B of X, J inverse. Okay. If we do that, we get the same, we have another factorization. We cancel here, and then by cyclicity of trace, the J and J inverse cancel. For J, this works for J inverse. And the idea is that you can use this degree of freedom to obtain another factorization where actually, where gamma, sort of the gamma of that factorization is small. So another factorization witnessing the fact that the gamma of n is small. Okay, so here's the theorem. It's due to probably from 2013, which is that if the PSD rank of M, actually this is easier way to say, which is just that for all non-negative matrices M, gamma of M is in most PSD rank times, times, I knew we needed this space, and we should have written that before. Okay. Times the maximum value of M. They actually proved it with rank squared, but Rick and her authors have a very nice survey where they give a much simpler proof and prove it with the tiny bound, which is the rank. Okay, so the point is that if I give you some factorization, it may not have this nice smoothness property where the norms of the factors is bounded. But by choosing this J, by choosing an appropriate J, you can rescale the space, or you can apply a linear transformation to the space so that the factors are bounded. And this is now we ran out of time. I planned a lot more. Apologies, but we ran out of time for the day. This is essentially the way that the PSD rank comes into play, although not quite. So, let me just okay. So let me state now this truncation lemma, and then we'll stop. So here's but it uses, I mean, sort of, this is the key step in the lemma. So if the PSD rank is at most R, then of M is at most R, then there exists, say, so we'll just stick to our old set of indices. There exist P's and Q's such that, first of all, MSX minus trace PS Q of X is at most delta for every S and X. So then for every delta greater than 0, the following holds. There exist maps which don't give a factorization, but are very, are close. So in L infinity norm, this is the L infinity distance to M of this matrix is small. And we have the following bounds. So the operator norms of okay. So first of all, the p's are sort of in isotropic position. So when you average over the p's, you get the identity matrix. This you can sort of always achieve for free. And then we have the following properties that the eigenvalues of p and q are bounded by, say, r squared over delta times the maximum entry of m. And then the second property, which is key, is actually that. Sorry. Let me say it this way. So in fact, this is contained in. So let's say it this way. So the operator norm. So these matrices are bounded. This is the operator norm. This is the trace norm. It's not so important. What's more, okay, but it's important the norms are bounded, and moreover. The maximum eigenvalue of Q, so basically this is the PSD ordering. The maximum eigenvalue of Q is at most r squared divided by the dimensions. The point here is that this value of K I don't care about. Okay, so you can say, so there exist these maps, there exists some K. Now we forget about what K is. I only care about the operator norms and the fact that, that the maximum eigenvalue of Q is, notice that it's very small. So whatever the sort of, it's like okay, so this factor which we can pay times 1 over the dimension. But this is the claim, and we'll stop now. So maybe we shouldn't have done it because there's no time really to explain it. But the first thing is that this is just yeah, okay, so I'll explain it. But this is I'm not really going to explain it. That's in my defense. This is a simple consequence of this theorem. That's the first thing. So like this contains most of the content. But the main point, the main point of this is that now we replace this algebraic condition on the factorization just by an analytic condition, and I no longer care about the value of the dimension, only about various norms that arise there. So let's stop there. And now the point is that once we're in that situation, then we can next time approximate b by a low degree squared. Okay. So questions? You should probably ignore the truncation lemma and just think about this. It's the fact that you have this analytic relaxation for rank. Yeah. Sorry.
Is this analytic PSC rank efficiently computed?
No, actually. I don't know how, and there's a reason that it probably shouldn't be efficiently computable. If you look at sort of factorization norms for like operators through a Hilbert space, so where you don't worry about if you look at factorization through a linear space instead of through a cone. Okay, so here we require these things to lie in a cone. If you consider, say, a factorization just through a linear space, let's say through Euclidean space, then you can compute the factorization norm using a semidefinite program. This one, you cannot do it in an obvious way, and I think there's a reason that now I'm blanking on why, I think there's a reason you should not be able to do it. I'm trying to remember if there is some, if anybody sort of like, there's a book of David and Eric of the PCP theorem using sort of operator factorization. And what comes up there is that sort of like, it should not be the case that their norm is computable. And I think this suffers from the same, or efficiently, in polynomial time. I think this suffers from the same thing. So maybe I might bet that it's empty hard to compute this norm. You had a question.
In condition 1, the norm of P of S should be with star, right?
Doesn't,
Is it the other way around as in the definition of gamma? Because
well, again, I mean, the definition of gamma is, I mean, we could interchange their roles. I was dumb to make the, for some reason it would be easier to make the indices S and X. But this is a definition for a general matrix. You can interchange the roles of P and Q. It has nothing to do with those.
yeah, I see.
But a larger point is that as long as these are, you know, the important thing here is these are bounded by a polynomial in R. Oh, actually, so here I guess it's no. So here I guess it's important that okay. Here it's in here now that the dimension of these things is not bounded. It's important to keep track of their of whether you want the trace norm or the operator norm. But this this version is correct, and it is the one that I want to have there. Yeah.
So I was wondering, so in the truncation lemma, so I guess you kind of have like three conditions, right? Like the expectation of S, P of S is the identity, and then the 1 and 2. So let's call them 0, 1, and 2. So I'm just wondering, like, so maybe each one individually you can get, you know, for free. So I'm wondering, like, where the approximation comes in. Is it that you can't get? Is it just you can't get all three of them together?
No. Getting this one is hard because you right. So how do you get this one? You would want to take your starting. You would start with a factorization witnessing this, and then you would want to invert. Then basically, suppose that factorization involved, you know, instead of P, it involved A. Then you would want to multiply by the inverse of this matrix. Like you multiply by the inverse. So if you define A to be this thing, where A is coming from this factor, from the assumed factorization, you want to multiply by the inverse of this matrix.
Yeah.
So you need to know something about the smallest eigenvalue, and the smallest eigenvalue could be 0. I mean, there's no reason the smallest eigenvalue is not 0. You can arrange it so that easily. So the point is
0. Couldn't you get a smaller size factorization?
it's okay. It could be tiny. The point is you don't have any lower bound on the eigenvalues.
Right.
So if you want to multiply by the inverse, you're going to make the norms like unbounded. This is
the problem is controlling that one and the 1 at the same time.
The problem is, I mean, well, if you want this condition, the way that seems obvious to do it is you now, you know,
right, multiply them.
you now define P of S like this.
Right.
And then you define the other side with A to the 1/2 and A to the 1/2. Now you want to bound anything, the operator norm or the trace, you know, the operator norm of this matrix. You can't do it unless you know something about the minimum eigenvalue of A. So of course, what do? You just add a small multiple of identity to A, then you pick up some error, and everything works fine. So it was like that's the truncation. You just shift the bottom of the spectrum.